Here in this bonus video, I'd like to go through the mathematical details of a few things that I glossed over in the main class videos. So these are things for class number 27 and 28. So there's three questions that I want to answer in this video. The first is to give an argument for why, if I take some arbitrary wave function and expand it as a sum of stationary states, why those expansion coefficients are given by this inner product between the stationary state psi sub n and my arbitrary wave function. The next question I want to answer is why, assuming I have a properly normalized wave function, is it the case that the sum of all my coefficients modulus squared has to be 1? And finally, I want to give the details behind an argument for if you calculate the expectation value of the Hamiltonian or of the energy operator, you'll get this. So you'll get the sum on n of E sub n times modulus squared Cn, which is an argument for interpreting C sub n modulus squared as the probability of measuring the particle's energy to be E sub n. Okay. So the reason I'm presenting all three of these arguments together is that they all are actually they all go in a pretty similar way. And it turns out they all depend on the orthogonality of the stationary states. So come along for the ride, and let's see how this all works out. All right, so let's start with argument A. Okay. So a line here. So let's start with our expansion coefficients C sub n. Okay. So we begin with being able to write our arbitrary wave function as the sum of stationary states. So I'm going to take f of x to be my arbitrary wave function here, and we know that this can be written as a sum, and it's a sum from n equals 1 to infinity, but I think you know that, so I'm just going to suppress that, and we know that that's written as a sum of psi sub n's, where, if you remember, these are our stationary states. The question is, how do I find these coefficients, which are buried here in the sum? The key is to use orthogonality. All fixed, yes. So the idea is the following. And what does orthogonality mean? Remember, orthogonality says that if I have the inner product, so if I have psi sub, let's do m, so stationary state psi sub m star, multiplying stationary state psi sub n of x, I'm going to write this bigger so that you can clearly read that that's an m and that's an n. The second one's an n, Well, this equals 1, 1 if m equals n, and 0 otherwise. Whoops. And that's going to be the key. So if we want to use this, we're probably going to have to insert an integral in here. So we basically inner product both sides. So inner both sides. And if we do that, that gives me, so on the left-hand side, I have, so I'll do, I'll hit it, I'll come in with m, on the left. So if I do integral 0 to L of psi m star of f of x dx, and then I'll do the same thing over here. To the right, I'm going to integrate 0 to L, and that's going to be a psi m star of x now times the sum cn psi m of x dx. Now, this may seem like a lot to unpack, and it's sort of not pretty, right? It's got this interval of this giant summation. So I don't think I've mentioned it a ton in class yet, because we haven't done too many of these. But my advice to you, if you're ever confused about some nasty looking thing involving a summation, it almost always helps to just write out the first couple of terms. And then it'll usually be easier to get some intuition for what's going on. So let's crank on the right-hand side a little bit. So we still have our integral here. And so I'll just write out the first few terms of the summation. So that's going to be c sub 1 psi 1 x plus c2 psi 2 x. And maybe I'll do one more for kicks, c3 psi 3x plus dot dot dot. And I've got my dx just fitting on off the page. Okay. Okay, so this doesn't look quite so bad now, right? Because notice, right, I can distribute, right, I have just, psi sub m star multiplying a whole bunch of terms. You know from calculus that I can just split this integral up so that I can just integrate it term by term. And what's more, there's a constant c sub c1, c2, c3, etc. appearing in each term. And I'm perfectly allowed to factor that constant out of the integral. So just because this is the first one we're doing, I'll write out the next step explicitly. And let me see, I think I'll do the rolling over technique here. So we see, and I need to get, okay, I think, there we go. Okay, so if I roll that over, so I'll write out the first couple of terms sort of expanded and then write out the, sort of go back to summarizing this using sigma notation. So that gives me, what do I have here? So so I'll do the first one, it's C1, integral 0 to L psi m star of x, psi 1 x plus C2, right? Psi, right, C2, interval 0 to L, right, psi m star, psi 2x, and I think dx plus dot dot dot, and I think you get the picture here. So if I try to summarize this, right, I can really write, I have a whole bunch of terms of this sort. I really have have the following summation. So I really have a sum on this time n, so I'll use n as my index. I have c sub n times my integral from 0 to L of psi m star psi n of x dx. Let me fill in the left-hand side here. So that's my integral of psi m star of x times my arbitrary wave function f of x dx. And that of x is a little too small. I'm sorry about that. But now, right, this is where the orthogonality comes in a critical way, right? Because we have a whole bunch of these. Just look at one of these terms, right? So I think you can see, like from the form of this integral, if m happens to be equal to 1, well, this integral by this normalization of stationary states goes to 1. But if m isn't equal to 1, we have the case down here where, by orthogonality, this integral vanishes. In fact, out of this entire sum, there's only one term that's not going to vanish. So the only surviving term is the term for which m equals n. So the only term that's non-zero by orthogonality is the one where m equals n on the right-hand side here, right? So, right, and again, if you want to sort of convince yourself of this, just think about what that would be. Just think it might be easier to think about this from the term by term right out over here. So again, if, for instance, now if m happened to be 2, right, then uh, right, this term would survive, but otherwise it would go away. So, right, this then lets us simplify, right? So I'm gonna write everything in terms of n now because that's the what index we're probably gonna be looking for. But m equals n, right? If out of stuff that survives, so I'm allowed to do that. So we have one surviving term, so we have c sub n in a row of 0 to L psi m psi, n, right? Because I'm taking that, I'm assuming this equality here, phi n of x dx, right? But this integral we know, right, by normalization, this integral equals 1. So we're left with, right, just Cn on the right here, and then dragging this over from before. Whoops, see my arrow's not visible, but okay, now you've got it. Let me put this page down over here. Rolling that over, right, and now I'm allowed to to replace m with n because because we're simplifying things here, and so if I do that, I end up with 0 to L psi sub n star of x f of x dx, right? And that proves what we said earlier, that the expansion coefficient is given by the inner product between the stationary state, the n-stationary state, and our arbitrary wave function. This is just like finding the x component of a vector by dotting it with with I hat. So, okay, so that's one down, two to go. So argument B, let's turn to that next. So argument B is for an so if for some arbitrary wave function, and let me write this as capital psi Townsend, right? If I use that and write it as c sub n little psi sub n, where that's a stationary state, is properly normalized, right? I claim that then my Cn's modulus squared equals 1, right? So why is this the case, right? So the idea is to is to do the normalization integral to both sides of this, right? So we know that 0 to L of psi x star psi x equals 1 by normalization. Well, if we do, all we need to do is to calculate this explicitly using this form over here. So let's see how that works. So I'll say we know that 1 equals now my integral from 0 to L. And I'll write this psi of x star. Now I have to pick an index to use here. The index I use is arbitrary because I'm ultimately summing over it, right? But I have to just be careful because I have two different expansions here, and so I shouldn't use the same index because I have to worry about cross terms. And again, I'll do the strategy of I'll write it out in sigma notation, but then also write out the first couple of terms to convince you of what's going on. So let's start with sum on M. This is the complex conjugate, so allowing for the coefficients to be complex. Again, N is really an index that doesn't actually matter here because it's being summed over, so I can call this index N or M or A, B, C, D, E, F, G, whatever I want. So psi m x here, so I have that sum multiplying my psi sub n, which is sum, okay, and I'll sum on n this time, Cn psi n of x, and this whole thing is getting integrated with respect to x. Again, this kind of looks like a hot mess, but it's usually easier to think about it if you write out the first couple of terms. So let's do that. So we have here, right, so we have C1 star psi 1 plus C2 star psi, and I'm not complex conjugating the stationary states because those are pure real for, at least for the infinite square well. So I'm allowed to do that. Psi 2 of x plus dot dot dot. And then for the second piece here, we have C1 psi 1 plus C2 psi 2 plus dot dot dot, and finally our integral dx. Now this looks like it's a nasty, nasty mess, right? Because I have, I have an infinite sum multiplying an infinite sum, but fortunately, it's not quite so bad because of orthogonality. So let's start writing out the the product here, and I'll just write out the first couple of terms. So I'll roll over to the top here, and yeah, so you can still see me. Okay, so let's do this. So we've got this enormous parentheses. So, right, multiplying two big polynomials, I have to just multiply every term by every other term. So let's first start with this term. So I have C1 star C1 psi 1 x. Let me just write this as psi 1 of x squared, right? So that's those two terms. If I multiply this term plus that term, and I have C1 star here, C2, psi1, psi2 of x, right? And similarly, I have this term, and then plus dot dot dot. So let's continue, and let's see, I can maybe put this on here. Let me just go to the next, continue the line. So both taking this term and multiplying it by that, I have C2 star, C1, psi2, psi1, and then finally I have C2 star, C2, and then psi2 squared plus dot dot dot, and this is all integrated dx. Now here's where orthogonality comes to the rescue. Right? Notice, right, I have sort of two types of terms here. I have terms where I have like the same index, right? So I have C1, C1, I have everything's 1 here. And then I have terms where I'm mixing the indices. So notice, however, because if I have psi1 times psi2, when I integrate that, by orthogonality, that term vanishes. Let's cancel this, right? So vanishes by orthogonality. Same thing applies to this term over here, because it's a product of two different stationary states. So that term also vanishes. In fact, I think you can now see that most of the terms are going to vanish. The only ones that don't are the ones that have the index identical. So let me write that out. So that gives me interval 0 to L, right? So now I have C1 star C1 psi1 of x squared plus C2 star C2 psi2 of x squared plus dot dot dot. I think you can see where this is going. When I integrate all of these term by term, right, so each one of those integrals is just going to go to 1 because my stationary states are normalized. SS are normalized. So this just turns into C1, and C1 star C1 is of course C1 modulus squared plus dot dot dot, etc. Right, so our integrals simplify, but we still know that this whole thing equaled 1 because we assumed that our wave function, our arbitrary wave function, was normalized to begin with. And so this leads exactly to the result we're trying to prove. Namely, we've now just shown that the sum on n of all of my expansion coefficients modulus squared, we've seen that that equals 1. All right, so that's 2 out of 3. We've got one more to do. I think I'll use a fresh page for this. Okay. So the last result I want to show here has to do with calculating the expectation value of energy, or more specifically of the Hamiltonian operator. So I want to find that the expectation value of my Hamiltonian, which, if you believe the formalism for calculating expectation values I introduced a while back, right, that's going to take the form for some arbitrary wave function, right, psi star h psi, and I integrate it over all its face, or since we're assuming infinite square well here, the wave functions are only non-zero between 0 and L. Let me just indicate that this is my arbitrary wave function. Okay. So the game is pretty similar to what we've done before, only now we end up invoking the time-independent Schrodinger equation. So once again, we'll write our arbitrary wave function as a sum of stationary states, right? What we have, our expectation value is all, just to save some writing, I'm not going to write the first one out as a sum just yet. So we have the Hamiltonian acting on the sum on n of Cn psi n x, and the whole thing we're integrating dx. Okay. Now, right, so again, this is the Hamiltonian just acting on a sum. So the Hamiltonian is an operator, right? So I'm allowed to, which involves some derivatives and stuff, that's all linear. I'm allowed to bring the Hamiltonian in here. I think you might be getting the hang of this, so I'm not going to write this out explicitly like I did the last one, but if it helps, by all means do that. So bringing in the Hamiltonian, I get psi star x. So I end up with, so I'm allowed to pull a constant, so moving the constants around, I get Cn Hamiltonian acting on psi n of x dx. Right. Now here's where we use the time-independent Schrodinger equation, because we know that the stationary states are energy eigenfunctions, right? So the TISE, right, says that the Hamiltonian acting on psi n is none other than my energy times my energy eigenfunction right back. So that lets me simplify this over here. So that now is a big simplification, because now we get rid of the Hamiltonian. So we now just get sum on n, C n E n psi n of x dx. Now, you might be sort of getting a hint of what's happening here. We're going to do exactly the same thing as we did in part B. We'll now write this psi star out as a summation and invoke orthogonality all over again. So this turns now, so I'll use a different index again so that I get all the possible cross terms. This is now sum on m c sub m psi sub m x, right? Times sum on n c n e n psi n x dx. But now, notice, right, that this is almost exactly the same as what we had the last time, right? So in the previous part, we had this, right? We had this thing with psi sub m multiplying this other thing with psi sub n. We have almost exactly the same thing, only we now have an extra factor of e sub n there. I think you can see how this game is played. I won't write it out in gory detail since we've done this already. So use orthogonality again as in part B here. And we get a whole bunch of, we get the sort of big infinite product, but most of the terms integrate to 0 by orthogonality, the only ones that survive are, in fact, the non-cross terms. So the only, oops, I forgot to complex conjugate that, there, got it. So the only surviving terms, have m equals to n. So that means that, so now if I'll just write everything in terms of n here. So the only surviving terms are the non-cross terms, so I have Cn star, I'll just pull all the constants out, Cn, En, right, and this is still summed over n, Cn star, Cn En, and now we have psi n of x quantity squared dx, right? And so I think you see where this goes, right? This now, right? So I can pull all the constants. I can take the integral inside the summation. Which I probably should have written that way in the first place. I can factor out the constants that don't depend on x. And then I'm left with integral of psi squared, psi sub n squared, which because the stationary states are normalized, this now just reduces to, right, c sub n modulus squared times e sub n. And that's exactly what I wanted to show by normalization. And that's exactly what I wanted to show. So we write our expectation value of the Hamiltonian. So suggests that the Cn modulus squared is, in fact, the probability of measuring the energy to be E sub n. So we've seen now how this sort of argument plays out in a couple of cases. In each case, the key step was to invoke orthogonality. We've used this idea here for the the stationary states, which are sine functions for an infinite square well. But this sort of general idea turns out to be much more general. It may come up again in E and M. This sort of orthogonality idea is called by David Griffiths, the author of the canonical upper-level E and M book. He calls this Fourier's trick, which is not a bad name. But yeah, so you can see how you've seen how that works here, and hopefully you can go on and apply it for yourselves if you need to in the future.